So first off, the title of my talk was Effect and Propagation of Silent Data Corruption in HPC Applications. But for many of you, the notion of silent data corruption may be a foreign concept. So what exactly is silent data corruption? So simply put, silent data corruption is any change of program, application state, operating system state that changes without the user, without the system, without anyone knowing it. This could be values that have been stored in memory, computations that are produced, and the operating system applications that we are running on these machines will go and reuse this data that has been computed incorrectly, that has been stored incorrectly, and it can potentially perturb the final results of the simulation, leading to wrong conclusions by application scientists. So how does silent data corruption actually occur? So the two main sources of silent data corruption in electrical systems are alpha particles through chip manufacturing and neutrons from cosmic radiation that's bombarding the Earth constantly. So it's experienced on a daily basis in large-scale machines. One result that is at this point rather old, but the Blue Gene L at Lawrence Livermore had an unprotected L1 cache, so anytime these effects happened, they were uncorrected. They instantly affected the program. They had a bit flip in the L1 cache, so just a single bit changed from 0 to 1, 1 to 0 at a rate of 3 to 4 hours. This is a per machine basis. Since then, every Blue Gene system has had some type of correction and detection mechanisms in all levels of cache. So but going forward, the machines are becoming more complex with result to transistors per chip, size of the machine, so we have more failure points. And also, in order to meet power requirements for extreme scale computing, we're going to be most likely running these processors and these chip components at something known as near threshold voltage. So the difference between low voltage and high voltage is now much smaller, so any type of change in the signal can easily flip a bit from a 0 to a 1. So the rate of silent data corruptions on future systems is expected to increase. So let's talk briefly about sort of classifications of errors or faults in the system. So faults occur, they lead to errors, and we can classify these in two forms. The best known form is these hard faults, which are reproducible. If I try to go to a web page and the server's down, I get the same error in my web browser every time I hit refresh. And the same if I try to communicate offline. These errors are reproducible. We know that they occur, and in the context of HPC, we can just recover using checkpoint restart. Because the error occurs, we'll fix it, we'll reboot a node, and we'll just recover again. Soft faults are the ones that you can't actually reproduce. They occur very transient. If they occur, they may not manifest in some type of detectable event, such as the application crashing. So they can lead to silent data corruption, which can later on propagate, affecting the results. So if you're not looking for these, they don't give any type of symptoms that they are present, so how do you recover? How do you know that you should recover? And so the first part of my research as a Blue Waters graduate fellow looked at how can you detect and recover from these silent errors. And I looked at it in the context of a linear solver algebraic multigrid. But I won't talk about that too much. What I will instead talk about is sort of what I feel is sort of lacking in the resiliency community. A lot of the papers, they talk about just the fact that we can detect errors with some percentage rate. Some errors were masked. But why were they masked in the application? Why were some errors masked? Why did some propagate and affect the final result, or propagate such that you were able to detect them? So I'm looking at the issue from a more fundamental level. So to facilitate my research, the fault model that I'm using is the memories themselves, caches, main memory, are protected by some error correcting codes. And this is just because that they are more easily protected than the actual logic on chip. So I say that faults will arise in processor computations, and they'll just manifest as register perturbations. So I'll inject faults by just having a LLVM compiler pass that will add code to perturb the results of some of the instructions as they are executed, and faults are injected randomly at runtime. And this fault injector is one that I developed and was released as an open source project as part of my Blue Waters graduate fellowship. So pretty much every resiliency paper will have sort of this is the worst thing that can happen graph. So here we have a solve of the linear solver algebraic multigrid solving a 2D Poisson problem, and I flip various bits in a floating point value, and I see what is the effect on convergence. Do we converge to the exact solution? In this case, for these experiments, we do. I was just affecting the residual vector, which gets used pretty heavily in the updating of the solution in AMG. And so we converge to the correct solution, but we take many, many more iterations depending on which bit was flipped. So if you flip bits in the mantissa, it's roughly equivalent to not even having an SDC. But if you flip bits in the exponent, you're looking at 4 or 5 times the number of iterations. What this could mean, I didn't crash the application, you still get the same result, it just takes longer. That error was saying that the error happened in some floating point. But when we express algorithms, we like to think that we express them, at least fundamentally, as mathematics. We understand the mathematics, but when we go to express them in code, and when that code is executing on a machine, it's not just pure floating point operations. We have fixed point arithmetic, control flow, pointer operations. So looking at just sort of the mathematics of the algorithm is a great first step to understanding how this error propagates. But understanding that it's not only floating point, there's other operations that are occurring in this system, so you really need to look at the interaction between all of these. So if we look at these in terms of propagation analysis, we saw the effects of floating point. And we know that floating point numbers are represented in sort of 3 fields. We have a sign bit, we have an exponent, we have a mantissa. And we can see that depending, if you really flip a bit in the exponent, then it's much more damaging than a flip bit in the mantissa. But for all these other ones, there's really integer type operations. So if we say we have a pointer, and if we flip a bit in this pointer, we either multiply or divide by a power of 2. So it's nice in the fact that I'm going to be indexing out of my address range, and I will easily generate a segmentation fault. So propagation analysis, if we corrupt data in fixed point operations, then we're likely to generate a detection event, and it's not really going to be leading to silent data corruption. Although there are some cases where it does, and that's really what I'm going to talk about in the rest of this talk. So a fundamental component of sparse iterative linear solvers is a sparse matrix vector multiply, and then iterative linear solvers would be used to solve PDEs at scale. So this is sort of like the building block of many HPC codes. So I look first at how it propagates mathematically, this error when it occurs. We look at what instructions, because we said it's not just floating point, and more of the real world, how errors propagate. So here we have a sparse matrix vector multiply. We have a single vector component that has become corrupted by some way. And when we do the sparse matrix vector multiply, we work it out, and we'll see that the number of non-zeros, let's say it's column I, the number of non-zeros in column I represents the number of entries in the matrix that would be using the corrupted value in which that error has propagated to. So if we think of this, if the matrix was fully dense, then we would have this entire vector corrupted. So the speed of propagation greatly depends upon the sparsity of the matrix. And like I said before, with a dense vector or dense matrix, then the entire vector has been corrupted. So we do get some benefit from the sparsity. So I ran a few thousand fault injection experiments on just a sparse matrix vector kernel, and sort of this is my classification of what errors were injected. So I injected at a random dynamic cycle through the execution that was uniformly distributed and in a random bit location. And about 45% of the injections were pointers, but this is reasonable because with sparse matrix vector formats, you have several levels of indirection until you actually get to the floating point values. And again, you have the fixed point arithmetic that would go along with adding into the actual load and stores. So if we look at the algorithm of a sparse matrix vector multiply, we see that the most complex line, the line that is executed most frequently, is the line that's receiving most of the injections. And again, we see several levels of indirection, some fixed point arithmetic that would flow in to the graph we saw previously. So when we did this, a surprising result occurred. We had some control flow divergence. I'll talk a little bit about that in a second. So I just showed you where we injected, but I never talked about how the errors have propagated or how we're looking at that. So the way that I'm looking at how errors are propagating is I duplicate this control flow graph of the sparse matrix vector multiply kernel. I have it in now two forms. I have a correct version that will be producing values that I'll compare against, and I have a faulty version which I will inject a fault into. And as the correct version is executing, I will log its loads and stores, the addresses and the values, and as the faulty version executes, I will be comparing the two to see if they mismatch either in the address or in the value that they were reading or writing. And so by looking at the loads and stores that have deviated and sort of the number of them as the simulation is going on, we can sort of get at, is the error propagating or is it being masked? So here is some results. This is the average number of loads and stores that were corrupted on a matrix that was greater than 99% sparse. And this is a single SPIMV operation. We see different instruction types on the x-axis here, and really independent of what type of instruction, we have between 2 and 3 loads and about 1 store being corrupted. And this is associated with the actual algorithm where we have load, 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 but really only a small number of stores. So that's the reason why this number of stores is less here. So if we look at sort of how this is used in sort of an iterative method fashion, we'll refeed that vector back in. It'll be updated somehow, and we see that the percent of loads and total loads and stores increases with the iteration count. So we can see that the error is propagating, and if we repeat this experiment with a denser matrix, we will see that the error propagates much faster. But not error propagates. I said that when we have bit flips that occur in fixed point arithmetic or pointers, they generate seg faults. So this is sort of a histogram of bit location. We have the least significant bit here, bit 0, the most significant bit, bit 64, and the frequency at which injections in those bits generated seg faults. So we see that the most significant bits have a high degree of generating a seg fault when you flip a bit in them. However, the low order bits, we are still flipping a bit, but the pointer is pointing to some data we have allocated. So we aren't generating some detectable event such as a seg fault, we're just reading incorrect data. And this is the interesting case here in which we are flipping the lowest order bit, and we're just reading unaligned data, and that actually leads to the most corruption that we occur. If we look at other classifications of instructions, here we see the looping control variables, I and j in the loops, and we only have just a single bit position value that affected that. That's because I was using unsigned arithmetic and we're flipping the signed bit. And that would cause us to be indexing incorrectly. Fixed point arithmetic, very much centered towards the most significant bits of that 32-bit integer. And here we can see sort of application's ability to mask error is I was feeding this vector back in, so you're multiplying this x of 0 by a, x of 1 by a, and you're essentially doing power iteration. And so you converge to the dominant eigenvector, and you can see we start having error propagate, but we also have seeing it being masked because we're converging to a fixed value. So it was easy to understand that in the context of feeding the vector back in, that we would have masking occur at some point if you iterate long enough. That's the whole nature of iterative methods. But for some applications, let's say molecular dynamics, you add an error and the simulation will just take off and propagate or deviate continuously as you increase time. So some conclusions I would like you to draw is if you think about silent errors occurring in your application, looking at the mathematics is a good first step. It allows you to reason about what components are important, but how this mathematics is expressed really paints the full picture. So if you look at how it is expressed inside a machine, it will give you more of the full picture. Yeah, so going forward, I would like I mentioned the in-body simulation. That's what I'm currently looking at now is seeing if I can say stuff about masking and propagation inside of in-body type applications. So I'd like to thank my funding sources. In particular, I would like to thank the Blue Waters Graduate Fellowship, providing me with some time to do this and my other research, and with all the support that they've provided me. And if there's time left, I'll take questions.
Any questions?
Yeah, or Abhinav.
So how do you
you get the control flow graph and like do you have a tool that you use for that? How do you duplicate it and run
LLVM.
that process?
I do all of my compiler stuff inside LLVM. So through LLVM, I'm able to grab the control flow graph and replicate it. Yes.
Is there any interest to look at bit flips as like a boundary condition?
Yeah. I mean, that would be something of interest that I could do. I haven't looked at it explicitly. Here, I just say they happen at some arbitrary point in the application. I guess I could ask you: is it sort of a permanent change to the boundary condition, or is it just sort of a transient? As I'm applying a boundary condition, how does that affect for a single time step? Which would be sort of what I would be getting at with the way that I'm currently doing my injection models. If you would use this in the context of some time-dependent simulation.
Yeah, I was exactly like a time dependent.
Yeah.
So
So,
it flips once and then it's reset
yeah.
the next time.
Yeah. So I have some work that's ongoing with plasma physics code that's being developed at U of I, but I haven't looked to see like the actual deviation of the values. I just done sort of the first order. This is where we inject at, and this is sort of the did we finish the simulation? Did we not? And that's some ongoing work that I'm going to be looking at this summer.